Question 91. Static equilibrium. A tightrope walker located at a certain point deflects the rope as indicated in the figure. If the weight of the tightrope walker is 150 pounds, how much tension is in each part of the rope? Since the question's telling us that the tightrope walker is in equilibrium, static equilibrium, we know that there is a balance here between the horizontal force and the vertical force. And we can see that with the tightrope, this vector right here, that these vectors are broken up into components, x and y components. As the y, and I'll change this to purple component, and then the x component. And that goes for the same for this part of the tightrope as well. You can see these are the y components here. It's supposed to be a y. These two y components are going in the opposite direction of the weight of the tightrope walker. So since the tightrope walker is in equilibrium, those two y components are going to equal 150, as you can see right here. And in the horizontal direction, we know that this length in the negative direction is going to equal this length in the positive x direction. As you can see from the horizontal force balance, that this value will equal this value. The first method I'm going to use is the head to tail method, which means I start with my first vector right here, and I'm going to take the second vector here, and I'm just going to connect it to the head of the first vector, which is the arrow. That's the head of the first vector. So these vectors have a magnitude and direction, and I'm not changing the direction or the magnitude. I'm just going to position it to the head of the first vector. And you can already see that these horizontal components are the exact same, just in opposite directions. And you can tell right here that this vertical component and this vertical component right here, they're going to be the sum of this component. Now, since the y and x axis is perpendicular to each other, we know this is 4.2 degrees. This will just be 4.2 minus 90 degrees, which that would be 85.8. We know this is 3.7 degrees right here. So, but there's a line as we draw this horizontal line. It's a rough line. So we know that since we move this vector, the angle is not this whole thing. It's like cut. As we move the vector, the angle is not this whole thing. But since we have two parallel lines right here, and here we have the transversal line right here, this purple line, that's the transversal. So this creates two corresponding angles. So this triangle is congruent with this triangle right here. So right here will also be 4.2 degrees, right? Because this is 4.2 degrees. So all we do now is add 4.2 plus 3.7, which would equal 7.9 degrees. So now I'm just going to put 7.9. Then add these two together, minus 180, and then we'll get this angle here, 86.3. And I forgot to add, but this is the resultant vector, which you connect from the tail of the first vector to the head of the second vector. So right here will be the resultant vector, which will equal, this will equal 150 pounds because our walker is stationary. So the sum of these two forces equals 0. And to find the magnitudes of these vectors right now, to find the tension, we can use the law of sine. So sine 7.9 over 150 equals sine, let's say 86. Since I want to find the link right here, 86.3 over, say, x. So to solve x, you just work out the math here. Now the tension on the left doing this will equal 1089. And then you just do the same thing on the other side. Just change this number here. Let's use an eraser. Change this number to this angle, 85.8. Doing that, you'll get almost the exact same number, except this will be 1088. And by doing it this way, I believe this method's the fastest, but you find the magnitude of the tension. Now the second method is using substitution, which this way is a little bit more complex, but you'll still get the same answer from the first method. For this, we're going to use these two equations right here. Like I said before, that equilibrium, the vertical forces is going to equal the weight. The horizontal forces are just going to equal each other. With the horizontal force, what we can do is set it up where we can substitute the tension to the right here and substitute into the tension to the left for the vertical force equation, so we can solve for t to the right. For the horizontal force balance, we know t left, right? We'll write that as t left. Or to make this easier, I'm just going to put TL for left, cosine, and we know what theta is on the left. It's 4.2 degrees. So what this is just right here for the length of the horizontal component. And I'm just going to make this a little bit smaller here. Then set this equal to t on the right, cosine, which would be the other angle, right? So these two are going to equal each other. But I want to figure out for tension on the right. So I'm going to divide this cosine 42 degrees on this side here, or 4.2 degrees. My bad. There we solved. Now we can substitute this in for tension on the left for the vertical force balance equation. So I'm going to figure out where to draw that. Right down here. I'm going to fix this as well. This should be more like this. So TR times cosine 3.7 degrees over cosine 4.2 degrees. From this, to not make this look messy, I just went ahead and pasted it here that what's in pink is substitution. The tension on the right that I got from the horizontal force balance. I plugged that into the vertical force equation. So instead of tension left, now it's tension to the right times cosine 3.7 over cosine 4.2 times sine 4.2 degrees. And this is how we're going to solve the tension on the right. Then after that, I factored out the tension to the right variable. And now you just calculate this right here, and then you just divide that. You do 150 pounds divided by this, which that should give you 1,088. That would be the tension on the right. Back to the equation up here, back to the vertical force balance. Now we can solve for the tension on the left. Just plug in t to the right times sine 3.7, 1,089. Now those are the two ways to find the tension in each part of the rope. First was head to tail method. This one is using substitution. Also, I just realized I meant to say up here, this is the horizontal equation, plugging it back into the horizontal. This here is the vertical, like right here. Taking t left and changing that to this in pink. I hope this video was helpful.